All right, so today we're going to start with part 2 of our stoichiometry lecture. And in this lecture, we're going to focus on what's called limiting reactant and percent yield. So limiting reactant and percent yield have a couple of important terms that we need to get straight before we actually start doing some math. So I'd like to review to you what we are actually talking about here with limiting reactant and percent yield and give you some problem strategies before we start trying to work problems. So first, the first rule of this lecture is you can't make fun of the fact that I can't draw. I'm very well aware of the fact that it's my main shortcoming in life that I cannot draw. So I'd like for you to imagine that in my spare time, I run a bike shop. Okay, I don't, but let's just say that I do. And so my bikes that I make at my bike shop are just regular old standard bikes. Okay, they aren't a two-seater bike. They don't have 4 wheels. They don't have training wheels, nothing like that. So 2 wheels, a handlebar, and some seats. So let's say that in order for me to make this world-class super speedy bike here, I order parts in 3 different sets. Okay, I order frames, so that's this piece. So there's my frame. Let's say that I order seats. Here's a super comfortable seat for your bike. And let's say that I also, sorry, my slides flip back and forth on me. So if that gets annoying, trust me, it's annoying me too. All right, so I have frames, I have seats, and I also purchase tires. Okay, so let's say back in my storeroom, let's say that I have 20 frames. Let's say that I have 15 seats, and let's say that I have 10 tires. Okay, so when it comes to actually producing bikes, I'm going to have a limited number. Oh, I went back too far. When it comes to actually producing bikes, I'm sorry, you guys, having some technical difficulties over here. So bikes produced. So if I only had to worry about my frames, I would be able to make 20 bikes. If I only had to use my seats, I would be able to make 15 bikes. And with my tires, this one's kind of tricky. I couldn't make 10 bikes out of my tires. I would only be able to make 5 bikes because of the numbers of tires I have. Now, in the real world, I don't just use one reactant, one piece at a time. I have to use all 3. And so that means that I'm theoretically only able to produce 5 bikes. And so that means that I am limited in the number of tires that I have. I'm going to have excess frames and seats. The excess reactant does not affect the number of products that I can make. Now, I say that I theoretically can make 5 bikes because what happens when I go back into my storeroom and one of the bikes or one of the tires has an unrepairable hole in the tire? Then I'm not going to be able to make 5 bikes. I won't be able to make that many. So I hope this example helps you to rationalize the difference between the following definitions that I'm going to give you. Okay? So the first definition that I want you to write with me is a limiting reactant. A limiting reactant is going to run out first and stop the reaction. It's going to run out first and stop the reaction. If you can't read my handwriting, I'm sorry, I guess that's another shortcoming that I have. So limiting reactant runs out first and stops the reaction. Therefore, it controls how much product is made. So the limiting reactant is the most important reactant. It tells us the maximum amount of product that can be made. Now, I want to kind of highlight something here for you. Back here, the maximum amount of bikes that I could make is 5 bikes. You said, but if you look up here, 20 bikes is definitely bigger than 5. But you forget, I can only make a maximum of 5 bikes because I have run out of tires. So technically the maximum amount is the lower amount of your product that you're going to make, just because you will always run out. No chemical reaction is going to just keep taking place and keep taking place. Okay? You're going to have an excess reactant. Sorry about that. Your excess reactant. You have more than you need. I'm really sorry about this. You have more than you need. This does not control the amount of product. The excess reactant is just extra. It's there. We still need it to take place, but I just have more than I need. Now, you're going to get a new formula that you'll need to write on your formula sheet and you'll need to memorize for your SOL test and for your unit test. Percent yield is calculated by using your actual yield over your theoretical yield times 100. Percent yield is going to tell us, did we waste anything? Did a mistake happen, or is the reaction just of the nature to not produce as much? So you want to produce 100%, kind of like you would like 100% on your next test. So let's talk about what each of these pieces mean. So first off, your theoretical yield is how much product would be produced in a perfect world with no error. It comes from the math with your stoichiometry problem from your balanced equation. So the theoretical yield is the maximum amount of product, but the catch is it comes from your limiting reactant. Maximum amount of product as calculated from your limiting reactant. So theoretical yield is the maximum amount of product as calculated from the limiting reactant. It is what could happen as long as nothing bad in the real world happens. Kind of like how I mentioned, one of my tires might just have an unrepairable hole in them. So the actual yield is going to be how much produced from an experiment. So the actual yield comes from an experiment. But here's the catch. You're working word problems. You're not actually going into the lab and carrying out these chemical reactions. So the actual yield is going to be given to you in the problem. But the theoretical yield is what you calculate. So one of the main ways that I try to think about and rationalize these two words is just by labeling out my chemical equation and doing a really good job of examining what I have given to me in the problem. Okay, so problem strategies. If you work a problem that says that it wants you to find the limiting reactant, I'm going to label it lim react. So label limiting reactant. There are many ways. So if you go to YouTube and you look for other videos on how to calculate the limiting reactant, you'll find many methods. I'm just going to teach you one of those that has worked best for me in the past. So you're going to do two stoichiometry problems. Two stoich problems. Okay? You're going to go from reactant. You're going to go from reactant to product, for each given amount of reactant that you have, okay? And then the maximum amount of product is technically the lowest amount. Maximum amount of product is the lowest amount. And so this is where we make that connection that it came from your limiting reactant, okay? So a limiting reactant requires two stoichiometry problems. Your problem is going to give you two starting amounts of reactants, and you're going to say, oh, but I didn't know which one to start with. Trick question, you technically use both. Make sure that you are going to the same unit and compound of product. You cannot compare two different compounds to one another. It's impossible. They are completely different. Okay? If you work a problem that says to find your theoretical yield, or the problem says something along the lines of theoretical yield, so the maximum amount of product or how many grams of this product could be formed, you're going to convert from the limiting reactant. So start with the limiting reactant, and then you are going to convert to the product that you are interested in. So again, these are all stoichiometry problems. So you really got to make sure that you're using a mole to mole ratio and that you are picking the correct compound to work with. Okay? Lastly, if your problem says that you need to work a percent yield, you're just going to plug and chug. Actual over theoretical times 100. And again, it's important to remember the actual is given to you in your word problem, whereas the theoretical is what's calculated from the limiting reactant. So the theoretical yield comes from calculations, the actual yield comes from experiments, but technically we're just reading word problems, so it'll be given to you in the problem. All right, so it's time to actually do something with these words. So I want you to open up to page number 6 in your unit book. Give you time to flip there. Page number 6. And we're going to look at number 2. Okay, so number 2 says, identify the limiting reactant when 10 grams of water reacts with 4.5 grams of sodium to produce sodium hydroxide and hydrogen gas. All right, so I hope that you realize and you learned from our first video that in order to do a stoichiometry problem, you have to have a balanced equation. So you might as well write that out with me here at the beginning. So I have H2O reacting with sodium, and it's producing NaOH, sodium hydroxide, and hydrogen gas. That's a single replacement reaction. And so if you want to take a pause to balance it, you can. Okay, your balanced equation should be 2 waters with 2 sodiums producing 2 sodium hydroxides and just 1 hydrogen gas. Okay, so it says identify the limiting reactant, and it gives me 10.0 grams of water, and it gives me 4.5 grams of sodium. So if you like to take the easy way out, you'll say, oh, 4.5 runs out first, it's smaller. Well, that's not technically the case, okay? We have to verify that using our math. So if you need to look back at our notes, when I find the limiting reactant, I do 2 stoichiometry problems from reactant to product, and I'm going to pick the one that gives me the maximum amount of product is technically the lower amount, and that came from the limiting reactant. Now, when you read your problem, it in no place says that I'm interested in a specific product. It just says identify the limiting reactant. So that means we get the option to choose this time, okay? So if you want, we can choose to go to, let's go to hydrogen gas, okay? So I'm going to work 2 problems. One, going from grams of water to, it again doesn't ask for anything in particular. So if we want, we can just stop at moles of hydrogen. Then I'm going to do another problem, starting with 4.5 grams of sodium, and I'm again going to work 2 moles of hydrogen. So if you want to take a pause in the video, you can set up your problems, and I'll set them up with you in a second. So try on your own. These are just stoichiometry problems, just like you've already done. All right, so hopefully you're able to get this far. You guys can start the process of setting up these stoichiometry problems. Moles of H2O to moles of H2. So maybe having a little bit of freedom in your word problem is making you uneasy. Sometimes your problem actually tells you, I'm interested in this compound, this product with this unit. This problem is just different, okay? So I know that 1 mole of water is the same thing as having 18.02 grams of water. And when you look at your mole-to-mole ratio, 1 mole of H is the same as 2 moles of H2O. So I type into the calculator 10 divided by 18.02 divided by 2, and so that gives me 0.277 moles of H2. So this tells me for all 10 grams of water to react, I'm going to produce 2.77 moles of H2. Great. Let's do this same problem, except we're going to start with moles of sodium this time. So 4.5 grams of Na, grams of Na to moles of Na, moles of sodium to moles of hydrogen gas. Another gram to mole conversion. So 1 mole of sodium is the same thing as 22.99 or 23 grams of sodium. 1 mole of hydrogen gas to 2 moles of sodium. So I divide 4.5 divided by 22.99 divided by 2, and that gives me 0.0979 moles of H2. So this tells me for 4.5 grams of sodium to be completely used, I'm going to make 0.979 moles of hydrogen gas. So now here's where we think. Just like with my bike example, I know that I'm only going to be able to make 0.979 moles of hydrogen. So this is our maximum amount of product, even though it's technically the lower amount, because 4.5 grams of sodium is the limiting reactant. Okay, so the whole point of number 2 is to arrive at this conclusion, that 4.5 grams of sodium is the limiting reactant. But I had to do 2 problems to prove it. Okay, let's try another one. Let's look at number 6 on page 6. Number 6 says, aluminum reacts with oxygen gas to produce aluminum oxide. And you said, oh, I have to write an equation first. So let's go ahead and do that. Aluminum reacts with oxygen gas, O2, and it's going to produce aluminum oxide. So using what we know from Unit 5, I crisscross, so that's Al2O3. If you don't believe me, remember Al plus 3, O minus 2. Hopefully that's an easy conclusion for you to make now. Okay, when I'm going to balance my equation, that's going to give me 4 aluminums with 3 oxygens and 2 aluminum oxides. Okay. So the problem says I have 200 gram sample of aluminum, so I'm going to go ahead and label it 200.0 grams of aluminum, and I'm reacting with 175 liters of oxygen, and it says what is the limiting reagent? Okay, reagent, reactant, those are just synonyms, no big deal. So I flip back to my notes. Letter A wants me to know my limiting reactant, limiting reagent, so I work 2 stoichiometry problems, reactant to product, and I'm looking for the maximum amount of product, which is technically the lower amount. Now, did number 6 ask me for a specific compound, a specific product? Well, we only have the one product to be worried about this time, aluminum oxide. Does it ask for specific units? Okay, so to figure that out, I'm going to look at letter B. It says, what mass of aluminum oxide could be produced? I know that mass is technically asking me for grams. So what I'm going to do, I'm going to work 2 problems, one starting with 200 grams of aluminum. I'm going to work to grams of aluminum oxide. And then I'm going to start with 175 liters of oxygen, and I'm going to again work to grams of Al2O3. So if you would, go ahead and set those 2 problems up. And then we will get started all together. So you try to get as far as you possibly can, pause your video, and work those problems on your own. All right, so if you've resumed your video, we are trying to check to see if you use the right problem strategy. So moles of aluminum, we're going to go to moles of Al2O3. Moles of Al2O3 to grams of Al2O3. So when I fill in my fractions, 1 mole of aluminum is the same as 26.96 grams of aluminum from the periodic table. Okay, when I look at my my mole to mole ratio, 2 moles of Al2O3 for every 4 moles of aluminum. Sorry, my slides keep flipping back and forth. And then my molar mass of aluminum oxide, 1 mole of aluminum oxide is 101.92 grams of aluminum oxide. So I would divide 200 divided by 26.96 times 2 divided by 4, or times a half, times 101.92. And that gives me, with 1, 2, 3, 4 sig figs, 378.0 grams of Al2O3. Now, I need to work my second problem. I'm going to start with 175 liters of O2. 175.0 liters of O2. Liters of O2. Moles of O2. Moles of O2 to moles. Again, I'm going to the same exact compound, moles of Al2O3, so that I can directly compare them. Moles of Al2O3 to grams of Al2O3. All right, so when I fill in my mole to mole ratios, here, mole to liter, I don't need the periodic table anymore. I just need mole to liter islands. So 1 mole is 22.4 liters. Sorry about that. My mole to mole ratio is going to be 2/3, and my molar mass of aluminum oxide, 101.92/1. So when I plug and chug, 175 divided by 22.4 times 2 divided by 3 times 101.92, and that gives me 530.8 grams of Al2O3. So we did all of that work to get these two values here and for us to put our thinking caps on. So technically, the maximum amount of product is the lower amount. So this is my theoretical yield that I'm circling. And that theoretical yield came from our limiting reactant. So 200 grams of aluminum is our limiting reactant. It will run out first and limit and stop our chemical reaction. So we technically answered A and B in using our one problem strategy. So letter A asked for the limiting reagent. That's 200 grams of aluminum. Letter B asked for what mass of aluminum oxide could be produced, and that answer is 378 grams of aluminum oxide. All right, let's try another one. Examples, examples, examples. Practice makes perfect. So let's look at page 7, and I would like for us to work number 3 altogether. Page 7, number 3. Okay, so this problem says octane burns in oxygen gas to produce carbon dioxide and water. When 320 grams of octane is burned in an oxygen-rich environment, 392 grams of water is recovered. What is the percent yield of the experiment? So, letter A, write a balanced equation. And if that wasn't obvious to you, you obviously haven't worked very many stoichiometry problems yet. Have to have that balanced chemical equation. So, octane is C8H18. They graciously gave me that chemical formula in the problem. It's burning in oxygen gas, and it's producing CO2 and H2O. So there's a good old combustion reaction. I know how much you all love to balance those. So if you will, just go ahead and pause your video. Make sure you get good practice in on balancing. So pause your video. If you are resuming, that means you've tried to balance your equation. So that is 2C8H18 plus 25 oxygen gas gives me 16 carbon dioxides and 18 H2Os. So do not be afraid of those big coefficients. Now, letter B says, determine the theoretical yield of water. That's interesting. Well, let's go ahead and label what we have. So we have 320 grams of octane. And then it says it's an oxygen-rich environment. So I'll write that under here. Oxygen-rich. And then the next number I see, I have 392 grams of water recovered. So that's a lot of numbers. Okay, let's think about what we need to do. So letter B says what? Determine the theoretical yield of water. So let's flip back here. To determine your theoretical yield, you're going to start with your limiting reactant and then convert to the product that you're interested in. Make sure that you are using the correct units and the correct chemical formula to get you there. Okay, so let's look. When I look at the products that I have, I'm interested in water. How did you know? Well, the problem gave me a unit that has to deal, or a value that has to deal with grams of water. Now, let's examine our reactants. I have 320 grams, and this tells me it's oxygen rich. It did not give me a starting amount of oxygen, so it's basically telling me that oxygen gas is in excess and so that means this here is my limiting reactant by default. So to find my theoretical yield, I'm going to convert from grams of C8H18 and I'm going to convert to grams of water. So that's one stoichiometry problem. So 320 grams of C8H18. And if you want to take a pause and try to work the problem on your own, you can always resume and then check and see how you did. It's very important that you grow in your confidence in these problems so that you can start doing them on your own. Okay, so I'm going to have grams of C8H18 on the bottom, moles of C8H18, moles C8H18 to moles of H2O, moles of H2O to grams of H2O. Okay, so when I fill in my mole-to-mole ratio, I have 1 mole. Oh, sorry. I know that has to be frustrating. So 1 mole is 114.26 grams of C8H18. My mole-to-mole ratio is 18/2. You can reduce that if you want. And then 18.02 grams over 1 mole. Sorry again. So when you plug and chug, that gives you 454 grams of H2O produced. So this is my theoretical yield. I'll label it TY. So letter C says determine the percent yield. So I use actual over theoretical times 100. And as you can tell from your notes that we made back here, my percent yield, the actual yield is given to me. The theoretical yield was what I calculated from my limiting reactant. So when I look at what I was given, I used this 320 grams already. Oxygen rich doesn't matter to me. So this has to be my actual yield. It's a given amount of product, so that's exactly what it is. So 392 over 454 times 100. So my percent yield, sorry about that, my percent yield is going to be 86%. So that's okay. That's like a B, right? You'll never turn down a B when it comes to your chemistry test, right? So it's pretty good. Obviously, we want 100%, but sometimes, especially with combustion reactions, that's kind of hard to come by. Okay, so let's look at number 5. Number 5 is one sentence, but it requires lots of work. And so these are the kind of things that hopefully you'll be able to infer after you get some practice. So number 5, determine the percent yield for the reaction between 5.0 grams of N2 and 1.0 grams of hydrogen gas if 5.5 grams of NH3 is produced. Okay, so right off the bat, have to have a balanced equation. N2 plus H2 produces ammonia, NH3. So when you balance, your coefficients are going to be 1, 3, and 2. This is technically in a textbook, so this would be called the Haber process. Okay, so the overall point of the problem says determine the percent yield. So that is percent yield, that's my goal, actual over theoretical times 100. So let's look and see what we were given. We were given 5.0 grams of nitrogen. We were given 1.0 grams of hydrogen. And then it tells me that 5.5 grams of NH3 is produced. Okay? Anytime it gives me an amount of product, that's my actual yield. So I already know that I have 5.5 over something times 100. So we have to calculate your theoretical yield. So if you look back at our slides a little while ago, remember theoretical yield only comes from your limiting reactant. So which reactant is limiting? And I hope you realize chemistry is not that easy. We can't just look and tell which one is the limiting reactant. We actually have to calculate it. So when you look back at your notes, finding a limiting reactant requires 2 stoichiometry problems. I'm going to convert from reactant to product and make sure that I follow all the nitty-gritty details to get me there. So if you do, go ahead and pause your video, try to set up your 2 stoichiometry problems on your own, and then resume to see how you did. Oops. Okay, so if you are resuming, you've tried your hardest. 5.0 grams of N2, grams of nitrogen gas to moles of nitrogen gas, moles of nitrogen gas. I'm going to go to moles of NH3, that's the product, moles of NH3 to grams of NH3. Okay, so 1 mole is going to be the same thing, 1 mole is going to be the same thing as 28.02 grams. My mole to mole ratio is going to be 2 over 1. And then my gram to mole ratio here, 1 and 1704. So I plug and chug. 5 divided by 28.02 times 2 times 17.04. And that gives me I need 2 sig figs, so 6.1 grams of NH3. And then I'm going to go again, so 1.0 grams of H2. And you guys are all like, man, oh man, why do I take chemistry? We work the same problems over and over again. But after a while, they kind of get fun, I hope. Maybe that's just me. So moles of H2 to moles of NH3. Oops. Moles of NH3 to grams of NH3. All right. So I fill in my blanks. 1 over 2.02. My mole to mole ratio is going to be 2 to 3. And again, 17.04 over 1. 1 divided by 2.02 times 2 divided by 3 times 17.04. And that with 2 sig figs gives me 5.6 grams of NH3. Okay, so we've reached the moment we've all been waiting for. What the heck do I do with these two products that I have? Which one matters? Okay, so remember my maximum amount of product is technically the lower amount. So this is my theoretical yield. And so that means that technically this 1 gram of hydrogen is my limiting reactant. So again, the problem didn't explicitly ask me for the limiting reactant, but I knew that I had to find it. So now I'm going to plug and chug. Actual over theoretical times 100. Sorry about that. So that is 5.5 over 5.6 times 100. And that gives me 98%. And that's an excellent percent yield. Okay. So before I turn you loose, I want to remind you of you're going to see a lot of these problems worded and asking for the same information, but just in different ways. Okay, so if you look at page 8, number 1, consider the following reaction. This one's nice and gives you the reaction, and it seems balanced. Plus 6 HBr produces AlBr3 with a 2 as a coefficient, plus 3 hydrogen gases. So it says, consider the following reaction. When 3.22 moles of aluminum reacts with 6.96 moles of HBr, what are the limiting and excess reactants? So you might be spoiled by the last couple of examples that have been explicitly telling us, oh, we need this product, you need to do this, you need to follow this step first. So let's just take it back to our notes. When the overall problem is saying find your limiting reactant, we worked 2 stoich problems from reactant to product, but it didn't give us a specific product that we're interested in. So remember, this is where you can pick. Since it didn't tell me what product I'm interested in, and it also did not tell me what units I'm interested in, you can keep it as simple as possible. So I pick hydrogen, and I'm going to say, you know what, let's figure out how many moles of hydrogen can be produced, because that's not a very long problem. Okay. So 3.22 moles of Al, moles of Al, moles of H2. And so that's 3 over 2 and would give me 4.83 moles of H2. I have 6.96 moles of Al, moles of Al, 2 moles of H2, and 3 over 6, and that gives me 3.48 moles of H2. So remember, the lower amount's the important amount, so this is my theoretical yield, and so that means that 6.96 moles of aluminum is my limiting reactant, and so that means that, oh sorry, this should be moles of HBr. I'm sorry, you guys. I make mistakes. I apologize if that got you confused. So the moles of hydrobromic acid is going to be limiting, and so our excess is going to be the moles of aluminum. So again, you can't just look at your starting amounts and assume that the lower amount is going to run out first. You actually have to do math. So big takeaways that I want you to see. You really have to become comfortable with your definitions. You should have definitely mastered how to use a mole to mole ratio. And then I think it's a really important skill for you guys to have is to figure out what all of your numbers mean at the starting of your problem. Is it asking you for a specific product? Is it asking you for a specific unit? So sometimes the problem tells you exactly what you want, and other times you all are given the slightest bit of freedom, but you still have to make sure that you are calculating all the necessary pieces, like your limiting reactant, your theoretical yield, and then finally you can plug and chug into your percent yield. So overall, hope the lecture has been helpful. Thank you for sticking with me through my random flipping of the slides or where my pen messes up. So I hope that didn't get too frustrating. Please feel free to go back and rewatch any section that you want. And as always, if you need extra practice, these are where you can go and look in your unit book. Go ahead and finish page 6 and 7, 8 and 9, and your study guide's on page 10 and 11. So the study guide's going to encompass part 1 and part 2 of my lecture series here on stoichiometry. And as always, feel free to see any chemistry teacher. We'll be happy to help you. Thanks for working hard.